Alright, here we go. We're going to go through one more example of mechanical equilibrium. Alright, this one will be a little different than the last one because this time we're not going to ignore the mass of our object. Okay, so let's go ahead and follow through the same procedure that we did before. Okay, number one, we're going to do a free body diagram. Okay, number two, we're going to choose our axes and identify our pivot point. Number three, we're going to make sure that we've broken everything down into components that we need to. Number four, if it is a mechanical equilibrium, the sum of the forces equals 0. 5, sum of the torques equals 0. And number 6, solve the dang problem. Okay, you'll notice that most of this is conceptual stuff, right? Being able to draw the free body diagram, choose the forces, choose the pivot point, right? It's not until later that we actually start to do the math. Alright, so let's go ahead and look at this one. Okay, you can read through the problem. I'm just going to go straight into it, so pause it if you need to. Alright, so let's look at our ladder. Okay, so here we've got a ladder on a wall. It tells us the wall is frictionless. Okay, now what that means is that we're going to have the normal force of the wall, because the ladder's touching the wall. I'm just going to label that force of the wall. Alright, now what else is touching our ladder? Well, the floor is, right? Now it actually gives us a coefficient of friction for the floor. So that means we're going to have the force of the ground, or the force of the floor, which is pushing up. And then if there was no friction, the ladder would slide to the left. So that means we've got to have some friction sliding to the right, pushing to the right, right? Trying to make sure that it doesn't slide. Alright? And then in this case, we're not ignoring the weight of the ladder. The weight of an object tends to act on its center of mass. Okay, so assuming that there's nothing causing our object to have to be balanced one way or the other, all the weight, we can imagine that it's acting at the very center of mass, which is right here. So that's where our 100 newtons is going to be. So that's the force of gravity pulling down on it. Alright, there aren't any other forces that are acting on my ladder, and so now we can go on and we can say, okay, where is our pivot point? Where are our axes? Okay, you can actually choose a couple of different pivot points, but the one I'm going to use for simplicity is this one right here. Okay, because that means that two of my forces aren't going to come into play when I look at torque. Alright, now I choose this pivot point because you can tell that if my ladder started to pivot about that point, it would require the ladder to start sliding, right? And we are wondering how far we can put it, and so how far can we put it before it starts sliding? So you can tell that any small change of rotation of torque or any movement, change of force, is going to cause it to start sliding. Okay, so that's why I'm going to choose this as my pivot point. Now these are already components, right? We've got up, we've got right, we've got down, we've got left, so we've already got all our components. So now let's go ahead and let's write out some of the forces, okay? So first let's go some of the forces in the x direction, okay? So we've got the force of the wall, which is going to the left, so negative force of the wall. We've got the force of friction, which is going to the right, so plus the force of friction. And that's all we've got in the x direction. Let's go on to the next one. Sum of forces in the y direction. Okay, so we've got the force of the floor, which is pushing up. And we've got the force of gravity, which is going down, so minus the force of gravity, which is that 100 newtons right there. And that's all our forces. Okay, so now let's go on to number 5, the sum of the torques. Alright, so sum of the torques is going to equal the torque of the two forces that are causing torque in this case. Remember, these two, the force of the floor and the force of friction, aren't going to cause torque because their distance from the pivot point is 0. Alright, so we've got this one, which is halfway up because that's the center of mass, and then we've got the force of the wall, which is all the way up. So you'll remember that torque is equal to the radial distance times the force times the sine of theta. And so obviously in this case we don't know what theta is, but we're going to find it out. So we've got the force of, this is our theta right here, that's the one we're paying attention to, right? So if I use this as my theta, that means that the angle of the force of gravity has to be the complement of theta, right? So that's going to be 90 minus theta. All right, so let's go ahead and do the torque of that force, the force of gravity. So that will be 2.5 meters, because it's halfway up the center of mass, times the force, which is 100 newtons, times the sine of the angle, which is 90 minus theta. All right. Now that is going down, which is going to cause my ladder to go in a clockwise direction. All right, so that'll be positive. And then we got the force of the wall that's pushing out this way. All right, so the force of the wall pushing this way, which is going to cause my ladder to go counterclockwise. All right, so the counterclockwise motion then is going to be minus. So the radial is 5 times the force, which we don't know what that is yet, times the sine of theta. Now by alternate interior angles, that's going to be our actual theta that we've designated down here. Alright, so we've got our equations set up. So now we can go ahead and go in and start solving. So we can look at the numbers that we have and the forces that we have. Alright, we know that each of these should equal 0. Alright, so I'm just going to go in and put the numbers in that I have, and then we'll figure it out from there. Alright, so in the x direction, we've got the negative force of the wall, and I don't know what that is yet, plus the force of friction. Now you'll remember that the force of friction is equal to the coefficient of friction times the normal force. Now the normal force here is the force of the floor. So that will equal that plus the coefficient of friction, which is 0.4, times the force of the floor. And those added together should give me 0. Alright, now I don't know what either of those are yet, so I can't really solve that. So let's go ahead and go into this one right here. Alright, so let's solve this one. We'll say we've got the force of the floor minus the force of gravity, which is 100 newtons, which has to equal 0. So now I notice that I can solve for the force of the floor. So let's go ahead and we'll add 100 to both sides. So the force of the floor has to be equal to 100 newtons. Now that I have the force of the floor, I can now put that in up here, and I can solve for the force of the wall. So negative force of the wall plus 0.4 times 100 newtons equals 0. 0.4 times 100 is 40, so that means that the force on the wall has to be negative 40 newtons, or 40 newtons. So force of the wall, subtract the 40, divide by the negative, is 40 newtons. Alright, so there we go. We've got the force of the wall, we've got the force of the floor. Now we can put this into our torque equation, because to get that distance that we're looking for, we need to know the angle. Now something I'm going to do that hopefully you guys are familiar with is, you should know that if you have the sine of an angle, then you can also take the cosine of its complement, right? So we can rewrite this as being 2.5 times 100, and then we're going to change this to cosine of theta, all right? And then minus 5 times 40 times sine of theta equals 0. We'll add this to the other side, so 2.5 times 100 times cosine of theta is equal to negative 5 times 40 times sine of theta. I'm going to divide by cosine of theta, so I'll have sine over cosine, which is tangent, and I'm going to divide by negative 5 times 40. Okay, so then we will have, sorry, since I moved that over, that should be positive. So let's take 2.5 times 100, and then we're going to divide that by 5 and divide it by 40. So I've got 1.5. So 1.25, that's dividing these over, equals sine of theta over cosine of theta. Alright, so 1.25 equals tangent of theta, and so I can now solve for theta. So we'll go tangent inverse of the answer, and we get 51.3 degrees. And so if this is 51.3, we know the hypotenuse. We should now be able to find the distance. So we want adjacent over hypotenuse. So cosine of 51.3 is equal to the adjacent over the hypotenuse. So 5 cosine 51.3. And we get our answer, which is 3.12 meters. Woo! That was fun. All right, there you go. Hopefully you've got enough background now that you can do your homework.